how do we remediate sodic soils? Right? Remember, sodic soils contain a lot of sodium, relatively speaking. These soils are a little more difficult to reclaim as compared to saline soils because they are at low hydraulic conductivity. This is because sodium is a large ion surrounded by 6 water molecules, and when it gets in between clays, it causes clays to disperse, right? So aggregates disperse and water doesn't move through the soil readily. So there's some steps that you can follow, and they're somewhat similar, but there are a couple extra steps that need to take place as compared to reclaiming a saline soil. So here they are. Here are the steps. Number one, you certainly have to establish drainage. There has to be drainage. Water needs to move sodium out of the rooting zone. And the second step is you need to amend the soil according to a soil analysis. You can get this from a soil testing lab, but here is the kicker with a sodic soil. When a soil is affected by sodium, there is sodium on the exchange sites, which is causing the soils to disperse. And we need to remove sodium from the exchange sites. And how do we do this? You'll learn about this in this video, that we oftentimes add a calcium source that can readily dissolve in the soil solution. And when we do this, this helps correct the problems with soil physical properties, the dispersion. And I'll tell you right now that we oftentimes, in fact, exclusively use either a calcium source external to the soil or internal to the soil. Regardless of how the calcium gets into the soil, calcium has a +2 charge. The hydrated radius of calcium is smaller than sodium. And because of that and the +2 charge, calcium ions can pull soil particles together or cause aggregation and improve or increase pore space for improvements in infiltration of water, percolation of water, and aeration. Okay, so you establish drainage, you amend the soil according to an analysis that's performed. You're going to add a calcium source. You leach the sodium from the root zone with good water, and you soil test to determine success. And this looks good on paper. And I'll tell you a caveat. And the caveat is this, is that these types of soils oftentimes are sodic because of poor quality irrigation water. And so where are you going to get good water? Good luck. All right. So there's other ways that we can overcome this. But in this instance, it is a challenge. So I gave you a prelude on the previous slide, but how do we overcome this issue? We've talked about some of these points on the previous slide. Plentiful, good quality irrigation water, challenge. Good drainage, probably not a challenge. You can do this in soils, right? We do this here in Ohio. We have lots of soils that are tile drained. And then you have to add a soil amendment that provides a source of soluble calcium to remove sodium from the exchange sites. And I bring to your attention the Lyotropic series from Unit 4. So sodium, you see, is way over here on the far right, and calcium is more than in the middle. It's more to the left. We add calcium, or we use calcium that's already in the soil to do this, to kick sodium off exchange sites. We need to have excess calcium to exchange with sodium on exchange sites, and then we need to leach that sodium out of the root zone. And then the calcium that's present, because it's a +2 charge and the hydraulic radius is smaller, pulls particles together, causes aggregation. So the question is, what soil amendment can be used to supply soluble calcium? And I can tell you that it's likely not lime, right? So lime is a great source if you want to increase soil pH. But in this case, lime really doesn't work because these soils especially sodic soils, have a high pH. Adding lime won't affect the pH, and in fact, just adding lime by itself won't do anything to these soils because there's no acid source to dissolve the lime and kick acidity off the exchange sites. So we need to find another soluble calcium source because lime in this case won't be soluble. So what do? What soil amendment can be used to supply soluble calcium in this case? The amendment that we often use there's two of them. The one that we often use that we can add is gypsum, right? And gypsum is a salt. It's a sulfate salt, calcium sulfate. This will dissolve readily in water. And the reaction that occurs is shown in these pictures on the bottom right. On the left, you have a soil that has a clay that has quite a bit of sodium. The plants are suffering, and we add gypsum. It dissociates in the soil water, and calcium comes off. If we add it at the right amount, we can kick sodium off the exchange sites, and now we have clay on the exchange, or calcium on the clay sites or the exchange sites, sodium in the soil solution, and then we irrigate and leach. And this is what you see down here in the bottom panel. We initially start with sodium on the exchange sites. We add calcium sulfate, gypsum, to add calcium. That dissolves in the irrigation water, and the irrigation water pushes sodium out of the exchange sites or out of the soil or the root zone because calcium is replacing sodium. And then you end up with a soil that has very little sodium on the exchange sites and has more of these other cations on the exchange sites. This is one way in which we can remediate a sodic soil by adding gypsum. However, there is another way, and that's written on this slide. If you have a soil that is calcareous, which means that the soil already contains calcium carbonate or native calcium carbonate, the calcium carbonate in the soil can actually be dissolved by amending the soil with an acid, or more often an acid forming substance like elemental sulfur. Now, let me share with you how this works on the next slide. Okay, and there's the reaction. I failed to put up the reaction for calcium sulfate, but I talked about it, right? And if you want to write that down, that's fine. And I'll hold off for a second moving forward to the next slide. All right. Now let me move forward. So how does elemental sulfur work? In a calcium carbonate containing soil, we can dissolve some calcium carbonate by adding elemental sulfur. And elemental sulfur can be dissolved or altered to form an acid. And this is the reaction that occurs. So here's elemental sulfur. It's yellow. It comes in either powder formed or prills like you see here. And when you add it to soil, this reaction, by the way, takes some time to occur because of this. Here's elemental sulfur. It reacts with oxygen and water in the presence of microorganisms to form 4 free hydrogen ions and 2 sulfate ions. This, if you combine these two together on the right-hand side of this equation, is sulfuric acid. But it's the hydrogens that are doing the work. This is the acidity. You learned about this when we talked about the pH. We talked about pH and alkalinity way back in Unit 3. This reaction, one of the reasons why this takes some time is because it is dependent on microorganisms to force the reaction to the right. And microorganisms in soil react as a function of temperature and moisture. So if the soil is really dry and hot, this reaction does not occur. So this takes some time, but it does occur. And these products, 4 hydrogen ions and 2 sulfate ions, react with free lime in the soil. So here's the reaction with water. And then here is the 4 hydrogens and 2 sulfate ions from the previous equation above, reacts with lime in the soil, calcium carbonate, to form actually gypsum and water and CO2, right? And then the next reaction is basically identical to the reaction that was on the previous slide that I fast forwarded through. Water reacts with the soil that contains sodium on the exchange sites and in the presence of gypsum, which dissolves and releases calcium to exchange with sodium on the exchange sites. So now you have calcium on the exchange sites, free sodium in the soil solution, and this down arrow means we leach this out of the soil, just like this picture up here. And that's how you would remediate a sodic soil if you had good quality irrigation water and either no calcium carbonate source or calcium carbonate source in the soil.